Welcome back. Glad you could make it. It is good to have you here again, drifting with me through the vast, silent reaches of the cosmos. Tonight we are turning our attention to something extraordinary and invisible, something that does not shine, does not glow, and cannot be touched, yet shapes the entire universe in ways we are only beginning to understand. We are talking about dark matter, the silent architect of everything we see in the night sky. When you look up at the stars, it feels as though you are seeing the universe in its entirety. Twinkling points of light spread across the black velvet of space. Wisps of glowing gas and clouds of cosmic dust reveal themselves to the eyes of telescopes, and the planets of our solar system gleam with reflected sunlight. And yet, all of this visible matter is only a tiny fraction of what the universe actually contains. Beneath the twinkling stars and luminous galaxies lies a hidden ocean of invisible mass, a mysterious presence that we call dark matter. Dark matter is not dark because it is colored or black. It is called dark because it does not emit, reflect, or absorb light. It is invisible to all forms of electromagnetic radiation, from the radio waves that pass through space to the X-rays and gamma rays that reveal the hottest objects in the cosmos. It cannot be seen directly. It cannot be touched. It cannot be detected with ordinary instruments. And yet it is everywhere, permeating every galaxy, threading through clusters of stars, forming the scaffolding of the universe itself. Astronomers first suspected its existence over a century ago when they began studying the motions of galaxies. They noticed something peculiar. Stars far from the centers of galaxies orbited just as quickly as stars near the core. According to the laws of gravity that Newton had described, these outer stars should have been moving more slowly. The visible matter in the galaxy, the stars, gas, and dust, was simply not enough to hold these stars in orbit. Something unseen must be exerting a gravitational pull, something invisible holding the galaxy together like a silent, cosmic glue. This invisible presence was the first clue of dark matter. Over time, more evidence accumulated. When astronomers observe clusters of galaxies, they find that the total visible mass is far too small to account for the motion of galaxies within the cluster. Gravitational lensing, the bending of light around massive objects, also shows us the presence of mass that cannot be seen. Light from distant galaxies curves as it passes through regions filled with dark matter, revealing its invisible shape. Without this hidden mass, clusters of galaxies would fly apart, and cosmic structures would never have formed the way we see them today. Dark matter acts like an invisible skeleton for the cosmos. Galaxies spin within enormous halos of it. Clusters drift and interact under its silent influence. Even our Milky Way is suspended within a vast halo of dark matter, holding stars, gas, and dust together as they orbit the galactic center. It forms a web that stretches across the entire universe, connecting galaxies in an intricate cosmic network that is both beautiful and invisible. Without dark matter, the universe would look completely different. Galaxies would scatter into the void. The large-scale structure of the cosmos would collapse. The night sky, the stars, the clusters, and the delicate spiral arms of galaxies like ours would never have formed. But what is dark matter made of? That is a question that continues to puzzle scientists. It is not made of the atoms and particles that we know. It does not interact with light, electricity, or magnetism. It does not clump together like ordinary matter. Instead, it is likely composed of some unknown type of particle, one that slips through everything, passing undetected through planets, stars, and even our bodies. In fact, billions of dark matter particles pass through you every second without leaving a trace. Some scientists propose these particles are incredibly heavy, others imagine them as feather-light, and some theories suggest that dark matter may be something entirely new that does not fit into any framework we currently understand. Despite its invisibility, we can trace dark matter by its effects. Light from distant galaxies bends as it passes through regions dense with dark matter. This bending, called gravitational lensing, allows astronomers to map the unseen mass across the universe. It reveals enormous structures, vast cosmic filaments that connect galaxies in a complex web. Dark matter is not just scattered randomly. It forms patterns, fills the gaps between luminous matter, and determines the structure of the universe on the largest scales. Dark matter also plays a crucial role in the formation of galaxies. In the early universe, after the Big Bang, ordinary matter alone would have been too diffuse to clump together into stars and galaxies. But dark matter, acting only through gravity, pulled ordinary matter into dense regions, seeding the growth of galaxies and galaxy clusters. Without dark matter, stars may never have formed, planets may never have existed, and life as we know it would be impossible. Every star you see, every planet, every cloud of dust floating through space owes its existence in part to the invisible grip of dark matter. And yet, despite all of this, we still do not know its true nature. Experiments deep underground, in particle colliders, and aboard satellites continue to search for signs of dark matter interacting with ordinary matter. But so far, it remains elusive. Every discovery only deepens the mystery. Some theories suggest it could be a particle we have never imagined, or a new kind of field that fills space. Others even wonder if our understanding of gravity is incomplete, and dark matter is simply the result of unknown cosmic forces. The universe is quietly reminding us that most of reality is still hidden, that the cosmos is far stranger than we can see. Even in our own galaxy, dark matter is everywhere. The Milky Way floats inside a halo of it, stretching far beyond the visible stars, a hidden ocean that binds everything together. Invisible filaments of dark matter connect neighboring galaxies, guiding their motion and influencing their fate. The universe is vast and complex, and dark matter is one of its deepest secrets, silently sculpting everything we see, shaping the cosmos over billions of years, and reminding us that much of reality lies beyond our perception. Dark matter stretches across the cosmos as the silent framework of everything, shaping the stars, guiding galaxies, and holding the universe together without ever revealing its presence. It is invisible, elusive, mysterious, and powerful, a constant reminder that the universe is far larger, stranger, and more beautiful than we can ever fully imagine. The discovery of dark matter was not a single event, but a gradual revelation, unfolding over decades as astronomers peered deeper into the universe. In the 1930 seconds, a Swiss astronomer named Fritz Zwicky studied the motion of galaxies in the Coma cluster. He noticed that the galaxies were moving far too quickly to be held together by the gravity of visible matter alone. There had to be something invisible adding mass, something unseen that held the cluster in place. Zwicky called it dunkel materie, dark matter, though at the time his idea was largely ignored, considered too strange or speculative. As decades passed, evidence for dark matter only grew stronger. In the 1970 seconds, astronomer Vera Rubin studied the rotation curves of spiral galaxies. She noticed that stars at the outer edges of galaxies were moving just as fast as those near the center. This defied Newtonian expectations. Normally, stars farther from the mass of a galaxy should orbit more slowly, just as planets far from the sun move more slowly than those close in. The galaxy should have spun apart, but it didn't. Invisible matter must be there, wrapping galaxies in vast halos, preventing stars from flying into space, acting as an unseen cosmic scaffolding. But dark matter is not evenly spread out. It forms enormous clumps and filaments, invisible threads that stretch across the universe, connecting galaxies like the strands of a cosmic spiderweb. These filaments are not gentle. They are dense with gravitational influence, pulling matter toward them, shaping the evolution of galaxies, and sculpting the cosmos on scales we can barely comprehend. Every cluster of galaxies, every spiral arm, every filament spanning millions of light years is held together by this unseen mass. We can detect it only through its gravitational effects, its quiet tugging on the luminous matter we can see. One of the most fascinating ways we observe dark matter is through gravitational lensing. Light travels in straight lines unless something massive bends it. Massive objects like galaxies warp space-time, curving the path of light that passes nearby. When this bending occurs, distant galaxies appear distorted or stretched. Sometimes they form rings or arcs around the invisible mass. By mapping these distortions, astronomers can reveal the presence of dark matter, tracing the invisible structures that otherwise elude every telescope. It is a cosmic fingerprint, a way of seeing the unseen. The scale of dark matter is staggering. It outweighs ordinary matter by roughly 5 to 1. Everything you see, every star, planet, nebula, and galaxy, is just a fraction of the total mass of the universe. The invisible dominates. The galaxies we admire, the clusters we study, even the vast cosmic web itself are mere reflections of this hidden mass. Without dark matter, the universe would not look the way it does. Spiral galaxies would not spin. Galaxy clusters would not form. The universe would be a far emptier, quieter, and less structured place, a thin smudge of particles floating in space rather than the intricate and complex cosmos we inhabit. And yet, despite all this evidence, we still do not know what dark matter truly is. It does not interact with light, nor with electromagnetic forces. It does not clump like ordinary matter, does not form stars, planets, or clouds. It seems to interact only through gravity, whispering its presence through the motions of galaxies and the bending of light across billions of light years. Some theories suggest it is made of weakly interacting massive particles, known as WIMPs. Others suggest it might be composed of axions or other exotic particles never observed in laboratories. Some even propose that our understanding of gravity itself is incomplete, and that dark matter is a symptom of a deeper cosmic law yet to be discovered. The mystery deepens as we consider dark matter in our own galaxy. Our Milky Way floats inside a massive halo of it, extending far beyond the glowing disk of stars. Invisible to our eyes, yet its gravity governs the motion of every star in our galaxy, including our Sunday. The planets, comets, and asteroids of the solar system orbit within this invisible ocean, carried along by forces we cannot see but can measure. The dark matter halo is not uniform. It is clumpy and lumpy, like waves in an invisible sea, producing subtle variations in motion that astronomers can detect by studying the orbits of stars, pulsars, and gas clouds. Even more fascinating is the role dark matter plays in the evolution of the universe itself. In the moments after the Big Bang, matter was almost evenly spread. Gravity caused tiny fluctuations in density to grow, and in regions where dark matter concentrated, ordinary matter was pulled along. These dense regions became the seeds of galaxies and clusters, guiding the formation of the cosmos as we know it. Every galaxy, from the smallest dwarf to the largest spiral, owes its existence to the silent shaping hand of dark matter. Without it, the universe might still be a hot, diffuse soup of particles with no structure or complexity. Dark matter also stretches our imagination. It exists everywhere yet interacts with nothing we can detect. Billions of dark matter particles pass through you every second, imperceptible and silent. It forms the backbone of galaxies, guides the motions of stars, and shapes the grand structure of the universe. We can measure its effects, but not hold it, see it, or touch it. It is the ultimate cosmic paradox, everywhere and nowhere, shaping everything while remaining completely hidden. It inspires questions that reach beyond physics. Could dark matter interact with itself in ways we do not yet know? Could it form structures we cannot detect? Could it hint at parallel universes or hidden dimensions? Every discovery about dark matter deepens the mystery and expands the horizon of what we know and what we do not know. It challenges our understanding of reality and reminds us that much of the universe remains unseen, that the cosmos is far stranger than the stars alone suggest, and that the invisible is often the most powerful force shaping our reality. The story of dark matter is ongoing. Scientists continue to search for direct detection, to collide particles at extreme energies, and to observe the universe with ever more precise instruments. Telescopes scan the sky for the subtle lensing effects. Satellites measure the cosmic microwave background for imprints of dark matter, and underground experiments attempt to catch a whisper of interaction. Each experiment brings us closer, yet the mystery remains. Dark matter continues to hide in plain sight, a quiet presence guiding the evolution of the cosmos while eluding our grasp. One of the leading ideas is that dark matter is made of WIMPs, or weakly interacting massive particles. These hypothetical particles are invisible to light, and they rarely interact with ordinary matter, slipping silently through everything, including planets, stars, and our own bodies. WIMPs would have been created in the early universe, just moments after the Big Bang, and they would have persisted ever since, forming the invisible scaffolding that holds galaxies together. Despite decades of searching, we have not directly detected WIMPs, yet their gravitational fingerprints remain clear, shaping the motion of galaxies and the structure of the cosmos. Another fascinating possibility is that dark matter consists of axions. These tiny, nearly massless particles would also interact very weakly with normal matter. They could exist in enormous numbers, forming a cosmic ocean that flows through the universe, invisible yet pervasive. Axions are so elusive that special detectors, often kept deep underground or in extremely cold conditions, are designed to sense the faintest hint of their presence. If found, axions could explain many mysteries, including why the universe seems to have more matter than antimatter, and how the early universe cooled and evolved into the cosmos we inhabit today. Primordial black holes offer a more dramatic possibility. These are black holes that might have formed in the first fractions of a second after the Big Bang, long before stars and galaxies existed. Unlike the massive black holes at the centers of galaxies or the stellar remnants scattered across space, primordial black holes could be tiny, ranging from subatomic sizes to massive enough to influence galactic structures. If they exist, they could account for some or even all of the dark matter in the universe, silently traveling through space, invisible except for the rare occasions when they bend light or pull on nearby stars. There are also theories that challenge our understanding of gravity itself. Modified gravity models suggest that what we interpret as dark matter could be the result of gravitational laws behaving differently at cosmic scales. In these models, there is no hidden substance, but rather a subtle modification in how gravity works over vast distances. Galaxies would rotate as they do not because of unseen mass, but because gravity itself bends and stretches in ways we do not yet fully understand. These ideas remain controversial, but they remind us that dark matter is not just a particle mystery. It is a question about the very fabric of reality. Some scientists even speculate about hidden sectors or parallel universes interacting with our own. In these models, dark matter could be ordinary matter in a universe slightly offset from ours, exerting gravitational influence without interacting with light or normal matter. The notion is fantastical, yet it is rooted in serious mathematics and quantum theory. It suggests that the universe is far more intricate than what we can see, that there may be entire realms of matter hidden alongside the familiar stars and planets, influencing everything silently from the shadows. Observationally, astronomers continue to uncover hints of dark matter in unexpected places. Dwarf galaxies, small collections of stars orbiting larger ones, seem to be dominated almost entirely by dark matter. Their motions cannot be explained by visible matter alone, indicating that dark matter is not evenly spread but forms dense, invisible cores in these galaxies. Even massive galaxy clusters bend light in ways that reveal enormous clouds of dark matter, forming intricate shapes that have no luminous counterpart. The universe is like a vast puzzle, with visible stars and galaxies acting as pieces floating on top of an invisible framework. One of the most striking revelations is how dark matter has shaped the evolution of the cosmos itself. In the first billion years after the Big Bang, the universe was a hot, dense soup of particles and radiation. Tiny fluctuations in density, amplified by the presence of dark matter, created regions where matter could collect and condense into the first stars and galaxies. Without dark matter, this structure would not have formed. The universe might have remained a featureless expanse of gas and radiation, never coalescing into the complex cosmos we observe today. Dark matter is the unseen architect, silently guiding the formation of everything from the smallest star clusters to the largest galactic superstructures. Even within our Milky Way, dark matter influences every movement. The stars we see in the night sky, the motion of our sun, the paths of distant globular clusters, all follow invisible currents shaped by this hidden substance. If we could see it, our galaxy would be revealed as a luminous disk, floating within a massive, invisible halo, a glowing island in an ocean of dark matter. This halo is not smooth but lumpy, creating subtle gravitational ripples that can bend the paths of stars and gas clouds, like waves moving through an unseen sea. Dark matter also connects to some of the deepest mysteries of physics. It interacts with gravity, yet seems immune to all other forces we know. It challenges quantum theory and relativity, potentially holding clues to a unified understanding of the universe. By studying its effects, we might one day uncover answers to questions as profound as why the universe exists in its current form, why it has the amount of matter we see, and whether there are hidden dimensions beyond our perception. Every experiment, every observation, every measurement brings us closer to understanding dark matter, yet the mystery grows richer, revealing new layers and new possibilities. The beauty of dark matter is that it exists everywhere and nowhere at once. It passes silently through your body, through the earth, through every star and planet. It shapes the cosmos, yet leaves no direct trace. It is invisible, intangible, and mysterious, a force that reminds us how much of reality is hidden from view, how much of the universe operates beyond our senses. It encourages wonder, humility, and curiosity. It reminds us that the universe is far stranger and more magnificent than we can imagine, that what we see is only a fraction of what exists, and that the cosmos holds secrets still waiting for discovery. Scientists have constructed vast underground laboratories to search for dark matter, buried deep beneath mountains or in former mines. These experiments are shielded from cosmic rays and other background noise that could obscure the faint signals of dark matter particles. Inside these quiet chambers, detectors filled with ultra-pure materials, sometimes liquid xenon or germanium crystals, wait for the rare and delicate interactions that might occur when a dark matter particle passes through. These interactions are unimaginably subtle. A single particle might nudge an atom slightly, creating a flash of light or a tiny vibration that is recorded by sensitive instruments. Detecting such a signal is like listening for a single heartbeat in a stadium filled with cheering fans, yet scientists persist, patiently waiting for nature to reveal its secrets. Space-based observatories offer another approach. Telescopes orbiting above Earth's atmosphere can detect the indirect effects of dark matter on cosmic rays, gamma rays, and the motions of stars in distant galaxies. These telescopes survey vast regions of space, searching for anomalies that could hint at the presence of invisible matter. When a cloud of dark matter interacts with itself or with ordinary matter, it could produce energetic particles or subtle distortions in radiation, leaving faint footprints in the cosmos. By mapping these clues across billions of light years, astronomers build models of where dark matter resides, how it moves, and how it has influenced the formation of galaxies over cosmic time. Particle colliders provide yet another window into the mystery. High-energy machines like the Large Hadron Collider smash particles together at nearly the speed of light, recreating conditions similar to the earliest moments of the universe. In these collisions, exotic particles might emerge, fleeting and invisible, disappearing before they can be directly detected. But physicists can infer their existence from the energy and momentum left behind in the debris. Each collision is a miniature cosmic experiment, a chance to glimpse the building blocks of reality and perhaps even the elusive dark matter particles that permeate the universe. The search for dark matter is not just about detection. It is also about understanding the role it plays in cosmic evolution. By studying how galaxies rotate, how clusters of galaxies bend light, and how the large-scale structure of the universe is arranged, scientists can map the invisible web of dark matter that threads through everything. These observations reveal that dark matter is not uniformly distributed. It forms dense clumps, halo-like structures around galaxies, and elongated filaments stretching across the cosmos, connecting clusters and superclusters in an intricate cosmic lattice. The visible universe of stars, gas, and dust is merely a decoration atop this hidden framework, glowing islands in a vast, invisible ocean. Simulations on supercomputers allow scientists to explore these cosmic structures in exquisite detail. By inputting the laws of physics and the estimated properties of dark matter, researchers can watch galaxies form, merge, and evolve over billions of years in virtual universes. These simulations reveal patterns that mirror our own universe, suggesting that dark matter is indeed a fundamental component of reality. They show how massive halos of dark matter guide the motion of galaxies, how streams of invisible matter flow through clusters, and how the large-scale cosmic web emerges from tiny fluctuations in the primordial universe. Each simulation is a story told in numbers and gravity, a quiet narrative of creation written in the language of mathematics and physics. Even as experiments and observations continue, dark matter retains an air of mystery. It is everywhere yet nowhere, shaping the universe silently, leaving no direct trace, and interacting with us only through gravity. Its presence reminds us that the cosmos is more vast, strange, and intricate than our senses can perceive. It invites imagination and humility, suggesting that reality extends far beyond the familiar, into realms that are invisible, but no less real. Every star, every galaxy, every particle of ordinary matter is cradled by this unseen structure, moving in response to forces we cannot see but can measure. The pursuit of dark matter is also a story about patience and curiosity. Decades of experiments have yet to provide a definitive answer, yet each null result narrows the possibilities, guiding scientists toward deeper insights. It is a cosmic treasure hunt, where the treasure is knowledge itself, a quiet understanding of the forces that shape existence. As detectors become more sensitive, telescopes more precise, and simulations more detailed, the hope is that one day we will finally glimpse dark matter in its full complexity, revealing not just what it is, but how it has guided the formation and evolution of the universe from its earliest moments to the present. Dark matter, in essence, is a reminder that the universe has layers, some visible and familiar, some invisible and profound. It challenges our assumptions, stretches our imagination, and invites us to explore a cosmos where the unseen is as powerful and essential as the seen. It is a silent architect, a cosmic conductor, shaping galaxies and guiding the dance of stars without ever announcing its presence. It is a mystery, a question, and a story that is still being written, one experiment, one observation, and one insight at a time. Dark matter is not just a hidden scaffolding of individual galaxies. It is the thread that weaves the cosmic web itself. Across the universe, galaxies are not scattered randomly. They trace a vast, intricate network of filaments, sheets, and voids, stretching across billions of light years. This cosmic web is the large-scale structure of the universe, a delicate lattice where galaxies cluster along dark matter filaments, and enormous voids of nearly empty space separate them. Without dark matter, these structures would not exist. Gravity from visible matter alone is too weak to form such intricate patterns in the time since the Big Bang. Dark matter forms the backbone, the silent skeleton upon which luminous matter hangs, shaping the universe in ways that are invisible to our eyes yet unmistakable to careful observation. In galaxy clusters, dark matter dominates the gravitational field. These clusters are massive, sometimes containing thousands of galaxies bound together in a single gravitational embrace. When astronomers measure the mass of these clusters by observing the motion of galaxies within them, they find a surprising discrepancy. The visible mass accounts for only a fraction of the total gravitational pull. The rest comes from dark matter, invisible and pervasive, creating a gravitational field that binds entire clusters of galaxies together. This unseen matter dictates how galaxies move, how gas flows, and even how light from distant galaxies bends as it passes through the cluster. Gravitational lensing allows us to map this invisible mass, revealing shapes and concentrations of dark matter that no telescope can see directly, yet that influence everything we can see. The influence of dark matter extends into the formation of galaxy clusters themselves. Early in the universe, regions slightly denser than their surroundings began to attract more matter through gravity. Dark matter, unimpeded by interactions with light or normal matter, clumped first. These clumps formed the seeds around which gas accumulated, eventually igniting the first stars and galaxies. In this way, dark matter acted as a silent architect, shaping the evolution of the cosmos from the earliest times. Without it, the universe would have remained a nearly uniform soup of gas, with stars forming sporadically and galaxies never taking the grand shapes we now observe. Dark matter gave the universe structure, coherence, and complexity. Even within individual galaxies, dark matter's influence is profound. It affects how stars orbit, how spiral arms persist, and how gas moves through galactic disks. Observations of dwarf galaxies, the small companions orbiting larger galaxies like the Milky Way, reveal that they are often dominated almost entirely by dark matter. Their stars contribute only a tiny fraction of the mass, yet these stars trace the gravitational contours of an invisible halo. Studying these systems gives scientists a laboratory to understand dark matter's properties, from how it interacts gravitationally to how it distributes itself across different scales. Dark matter is not a single entity. Current research suggests it could be composed of exotic particles unlike anything found in the standard model of physics. Candidates include weakly interacting massive particles, sterile neutrinos, or even more exotic possibilities like axions. Experiments deep underground or in space are attempting to detect the faint interactions of these particles, hoping to reveal the true nature of this invisible substance. Until then, dark matter remains a shadow, detectable only by the way it bends light, tugs on stars, and structures the universe. On the grandest scales, dark matter forms colossal filaments connecting galaxy clusters across the cosmos. These filaments are tens or hundreds of millions of light-years long, like vast invisible highways guiding the flow of galaxies and intergalactic gas. Between the filaments lie enormous voids, regions almost entirely devoid of matter, where the density of dark matter is far lower. Galaxies in these voids are more isolated, evolving in solitude, while galaxies along the filaments experience richer environments, collisions, and mergers. Dark matter thus creates diversity in the universe, shaping both the solitary wanderers and the bustling communities of stars. Even in our local cosmic neighborhood, dark matter silently threads through space. It surrounds the Milky Way in a halo that extends far beyond the visible disk, influencing the motion of stars and globular clusters. It interacts only through gravity, leaving no direct trace of light, heat, or sound. Yet its presence is unmistakable, detectable in the subtle motion of stars, the bending of light, and the behavior of interstellar gas. Every step the Earth takes around the Sun, every orbit of our solar system around the Milky Way's center, occurs in a landscape shaped by this invisible mass. The mysteries of dark matter extend beyond structure and motion. It may also affect the evolution of galaxies themselves, influencing the rate of star formation and the growth of supermassive black holes. Some galaxies shine brilliantly with new stars, while others remain dim and quiet. The distribution of dark matter may be a key factor in these differences, guiding gas, fueling star formation, and shaping the life cycle of galaxies over billions of years. In a sense, dark matter is both a silent enabler and a cosmic conductor, orchestrating the rhythms of creation without ever being seen. Dark matter challenges our understanding of the universe and of reality itself. It forces us to imagine matter that cannot be touched, seen, or sensed in ordinary ways, yet that dominates the cosmos. It is a reminder of the limits of our perception, showing that most of the universe is invisible, silent, and profoundly mysterious. Every galaxy, every cluster, every filament of the cosmic web owes its form to this unseen presence. Dark matter is not just a substance. It is the hidden architecture of existence, the quiet sculptor of the cosmos, and a doorway to mysteries that may one day change our understanding of everything. Dark matter is believed to have emerged in the earliest moments of the universe, almost immediately after the Big Bang, and it has remained a silent yet powerful force ever since. Imagine the universe at that time as a vast, seething ocean of energy and particles, far hotter and denser than anything we experience today. In the very first fractions of a second, every type of particle imaginable was forming and vanishing in a chaotic dance. Light itself was trapped, bouncing endlessly between particles, unable to escape, while the fabric of space expanded at an incredible pace. In this seething primordial soup, the first traces of dark matter appeared, moving invisibly through the maelstrom, unaffected by radiation and almost completely aloof from the forces that dominated ordinary matter. Unlike the particles that would eventually form protons, neutrons, and electrons, dark matter did not interact with photons. It did not glow, it did not scatter light, and it did not feel pressure in the way ordinary matter did. In the chaos of the early universe, this allowed dark matter to begin gathering in regions where its density was slightly higher, forming invisible clumps that acted as the skeleton for the cosmos. These clumps, known as dark matter halos, became the frameworks around which gas and dust would eventually collect to form galaxies and clusters of galaxies. Without dark matter, ordinary matter would have struggled to come together at all, and the universe as we know it may never have formed its magnificent structures. The exact timing and mechanism of dark matter's creation remain one of the deepest mysteries in cosmology. Many theories suggest that it was created in the first moments after the Big Bang, during a period when the universe was unimaginably hot and dense. Candidates for dark matter include WIMPs, hypothetical particles that interacted weakly with ordinary matter, and axions, nearly massless particles that emerged during subtle phase changes in the early universe. Some scientists even consider that primordial black holes, formed from tiny fluctuations in the dense energy of the newborn universe, may make up a portion of dark matter. Whatever the case, these particles or objects settled into a stable abundance as the universe expanded and cooled, leaving behind the invisible scaffolding that guides cosmic evolution today. The universe's expansion played a crucial role in the development of dark matter. While ordinary matter remained tightly coupled to radiation, moving in waves and responding to pressure, dark matter was free to flow under the influence of gravity alone. Tiny overdensities in its distribution were amplified as the universe grew, creating the first seeds of cosmic structure. Gas and dust that followed these gravitational hints cooled and condensed to form the earliest stars. The galaxies we see today are therefore built upon a foundation of dark matter that was established almost at the very beginning of time. Every spiral arm, every cluster, and every vast cosmic void owes its existence to the unseen mass that began its journey immediately after the Big Bang. We can observe evidence of dark matter's ancient role in the cosmic microwave background, the faint afterglow of the Big Bang that permeates the universe. Variations in temperature across the sky reflect tiny differences in density from when the universe was only 380,000 years old. Dark matter enhanced these differences, allowing some regions to collapse more quickly than others. Without dark matter, the universe would have been far more uniform, lacking the rich tapestry of galaxies, stars, and planets that now fills the cosmos. Its gravitational influence set the stage for cosmic evolution long before light could travel freely or stars could ignite. Dark matter is also responsible for the large-scale structure of the universe. Imagine a three-dimensional web extending across billions of light years. The threads of this web are dark matter, while ordinary matter collects along them, forming luminous galaxies and clusters. This cosmic web, a direct consequence of dark matter's early creation, shows us that even the vast emptiness of space is shaped by something invisible and ancient. The dark matter that appeared after the Big Bang has guided the formation of every galaxy and every star system, quietly controlling the universe from behind the scenes. Even today, dark matter continues to influence the universe. It shapes the rotation of galaxies, holds clusters together, and bends light from distant objects through gravitational lensing, revealing its presence even though we cannot see it. Its origin in the first moments of the universe connects the tiniest fractions of a second to the enormous cosmic structures we observe now. It is both ancient and eternal, a silent witness to the unfolding story of everything in existence, stretching from the birth of time to the far future of the cosmos. The creation of dark matter right after the Big Bang is not just a question of when, but of how it has guided the universe's growth for over 13 billion years. It teaches us that the universe is not only shaped by what we can see, but also by the unseen, the hidden scaffolding that allows stars to shine and galaxies to spiral. By studying dark matter, scientists glimpse the earliest history of the cosmos and understand the invisible forces that continue to mold it. Its existence reminds us that even in the vast emptiness of space, unseen structures govern the destiny of everything. Dark matter remains one of the most profound mysteries in the universe. We cannot see it, we cannot touch it, and yet it outweighs all the stars and planets combined, making up roughly 85% of the matter in the cosmos. It drifts silently through galaxies, through clusters of galaxies, through the vast emptiness between, shaping everything while remaining completely invisible. Its gravitational pull is the invisible hand that molds the large-scale structure of the universe, guiding the motions of stars, galaxies, and clusters as if it were an unseen choreographer of cosmic dance. Even though it does not interact with light, its presence is revealed through its effects on the motion of galaxies. Spiral galaxies rotate far faster at their edges than expected if only the visible stars and gas were present. Without the gravitational influence of dark matter, these galaxies would tear themselves apart. The stars on the outskirts of the Milky Way are held in their orbits by an invisible mass that extends far beyond the glowing spiral arms. The galaxy's luminous core is but a tiny part of the gravitational story, the rest written by dark matter that envelopes it in an enormous halo, stretching tens or hundreds of thousands of light years into space. Clusters of galaxies, the largest structures in the universe bound together by gravity, offer another clue to the invisible matter that pervades the cosmos. Observations reveal that the galaxies themselves account for only a fraction of the mass required to hold the cluster together. The space between galaxies is filled with hot gas glowing in X-rays, yet even the combined mass of galaxies and gas falls short of what is needed. Only dark matter provides the extra gravity, the unseen scaffolding that holds entire clusters together, preventing them from drifting apart over cosmic time. Gravitational lensing further illustrates the reality of dark matter. Light from distant galaxies bends and warps around invisible mass, creating arcs and rings of distorted starlight, mapping structures that are otherwise hidden. These patterns reveal a cosmic web of dark matter filaments connecting clusters across millions of light years, a vast invisible network threading the universe. Dark matter also shaped the early universe. In the moments following the Big Bang, tiny fluctuations in density emerged in the hot, nearly uniform universe. Dark matter, unaffected by the radiation that dominated ordinary matter, began to collapse under gravity, forming seeds for galaxies. Ordinary matter fell into these dark matter halos, gas cooled, stars ignited, and the first galaxies were born. Without dark matter, the universe would have remained largely smooth, lacking the dense regions necessary for galaxy formation. Dark matter is both the skeleton and the unseen engine of cosmic evolution, guiding the formation of everything that exists today. Within galaxies, dark matter governs the motion of stars in ways that ordinary matter alone cannot explain. Dwarf galaxies, the small companions orbiting larger galaxies, are almost entirely dominated by dark matter. Their few stars and sparse gas are mere tracers within massive halos of invisible matter. By studying these small galaxies, astronomers can infer the properties of dark matter, mapping its distribution and understanding how it shapes motion on small and large scales. These tiny galaxies act like laboratories, offering a glimpse into the invisible structure of the cosmos. Dark matter is not uniform. It clusters, it flows, it forms dense regions and diffuse filaments. The cosmic web is made primarily of dark matter, with galaxies and gas tracing its invisible shape. Vast voids stretch between filaments, regions almost empty of ordinary matter but still threaded by dark matter. These voids highlight the contrast between what we can see and what exists beyond our senses. The universe is a mixture of light and shadow, the visible and the invisible, the known and the mysterious. Dark matter is the silent majority, shaping reality without ever announcing its presence. Detecting dark matter remains one of the greatest challenges in modern science. Scientists build enormous detectors deep underground to shield them from background radiation, hoping to catch a rare interaction with a dark matter particle. Particle accelerators recreate conditions like those moments after the Big Bang, searching for new particles that may account for this hidden mass. Telescopes scan the sky for faint signals from decaying or annihilating dark matter. Each experiment is a careful and patient attempt to touch the untouchable, to glimpse the unseen, to bring the invisible into the light of understanding. The influence of dark matter extends to supermassive black holes at the centers of galaxies. Its gravity shapes the inflow of gas, guiding star formation and influencing the growth of the largest black holes. It orchestrates the motion of stars in galactic bulges, affects spiral arms, and stabilizes structures that would otherwise be transient. Even on scales far larger than galaxies, dark matter guides the mergers of galaxy clusters, directing the cosmic flows that shape the large-scale universe. It is subtle, indirect, yet absolutely essential. Dark matter also challenges our imagination. It invites speculation and wonder. Could it interact in ways we do not yet understand? Could it be composed of exotic particles like WIMPs, axions, or sterile neutrinos? Could tiny primordial black holes from the earliest universe make up part of its mysterious mass? Each possibility opens new doors in our understanding of reality, pushing the boundaries of physics, astronomy, and cosmology. It teaches patience and humility, reminding us that most of the universe lies beyond the reach of our senses, yet affects us in every motion, every orbit, and every structure we observe. Even our own Milky Way is enveloped in a vast halo of dark matter. It extends far beyond the spiral arms, a gravitational cloak unseen by our eyes. Every orbit of our sun and the surrounding stars occurs within this halo, every movement subtly influenced by this invisible mass. The motion of neighboring galaxies, the stability of star clusters, the distribution of gas clouds, and even the paths of distant comets and dwarf galaxies are shaped by the presence of dark matter. Its influence is quiet but pervasive, a reminder that the universe is not as it appears, that reality is deeper, stranger, and more interconnected than we can easily imagine. The mystery of dark matter also touches on the fate of the universe. If the universe continues to expand indefinitely, dark matter will continue to shape the motion of galaxies, influence the formation of new structures, and interact gravitationally in ways we have yet to fully understand. Its presence may also hold the key to understanding dark energy, the force driving the universe's accelerated expansion. In the far future, long after stars have burned out, dark matter may remain as the silent framework on which the remnants of the universe drift. In essence, dark matter is the unseen backbone of reality. It is the invisible hand shaping galaxies, clusters, and the cosmic web. It is the silent witness to the birth and evolution of the universe. It is a challenge to our understanding, a puzzle waiting to be solved, and a reminder that much of the universe remains hidden, invisible yet profoundly real. Its presence teaches us patience, curiosity, and the humility to accept that what we see is only a fraction of what truly exists. It is a quiet, pervasive, and fundamental part of the cosmos, shaping the universe without ever revealing itself fully. Right now, as you exist in this very moment, dark matter flows all around you, silently weaving through everything you can see and touch. It is not part of your daily awareness. You do not feel it, you do not see it, and yet it is everywhere. It passes through the air you breathe, through the walls and furniture, through the atoms of your body, and through the very ground beneath you. Every object in this room, every leaf on a tree outside, every star in the night sky, is accompanied by the invisible embrace of dark matter. The presence of dark matter is overwhelming in its scale and subtle in its interaction, a paradox that defines much of the universe itself. Scientists estimate that ordinary matter, the stuff we are familiar with, makes up less than 1/6 of the total matter in the universe. The rest, 5 times more abundant, is dark matter, forming an invisible backbone for galaxies and clusters of galaxies. You are, in this instant, floating in a sea of this unseen substance. It drifts through you without interference, without notice, but it shapes the motion of everything around you. The Earth orbits the Sun as it does, the solar system orbits the center of the Milky Way as it does, and the stars themselves cluster in galaxies as they do, all because of the silent hand of dark matter. You are part of a universe held together by something you cannot see, something you cannot touch, yet whose presence is fundamental to your very existence. Imagine that around you stretches an invisible halo, a ghostly ocean surrounding the Milky Way, extending far beyond the stars you can see. This halo is dark matter, and it contains more mass than all the stars, planets, dust, and gas combined. Its gravitational influence dictates the motion of stars in their galactic orbits. It is a cosmic scaffold, the structure upon which visible matter is arranged. And while it shapes everything on the largest scales, it flows silently around each person, each tree, each mountain, threading through the molecules of your body without obstruction. The ordinary matter you see is just a tiny fraction of the universe. Most of the mass that exists around and through you is invisible, ghostly, and omnipresent. Dark matter is ancient. It began shaping the universe shortly after the Big Bang. Long before the first stars ignited, long before the first galaxies formed, dark matter was already gathering into clumps, sculpting the cosmic web that would guide the formation of all structures in the universe. And now, 13 billion years later, it still flows through the universe, guiding the motion of everything, connecting galaxies, anchoring clusters, and passing quietly through your very body as you sit, stand, or move. You are wrapped in the invisible architecture of the cosmos. Each moment, countless dark matter particles pass through you without notice, but their collective presence is immense. Even the Earth itself is moving through this invisible sea. Our solar system sweeps through the Milky Way at hundreds of kilometers per second, drifting through the dark matter halo surrounding the galaxy. You, sitting in your chair or walking across a room, are carried along with this immense cosmic current. The dark matter in the galaxy is not static. It flows, it drifts, and it forms structures on scales far beyond human comprehension. In a way, you are like a leaf floating in a river that you cannot see, surrounded by a current that has existed for billions of years, guiding the movement of stars, planets, and galaxies. The influence of dark matter extends beyond gravity. Its distribution determines the shapes of galaxies, the clustering of stars, and the formation of galaxy clusters. Without dark matter, the Milky Way would not have formed in the way it did. Our solar system, the Earth, and even you might not exist. The stars might fly apart, galaxies might fail to coalesce, and the universe would be unrecognizable. And yet you will never feel it directly. It exerts its influence silently, invisibly, and persistently. Every atom of your body exists within this vast, unseen network. Every breath you take, every step you take, every thought you have, is accompanied by countless dark matter particles passing through you at near the speed of light. You are encased in a protective ocean that has been shaping the universe since time itself began. And though it is invisible and intangible, its presence is inescapable, guiding the movement of everything from the smallest asteroid to the largest supercluster. Dark matter does not interact with light. You cannot shine a flashlight and illuminate it. You cannot hear it, feel it, or taste it. It is a cosmic ghost, present in massive quantities, yet silent and intangible. And yet it is fundamental. It is the reason galaxies rotate at the speeds they do. It is the reason clusters of galaxies hold together. It is the reason the universe has the shape and structure it does. And it is everywhere, including inside you, outside you, above you, below you, and all around you. When you imagine the universe, do not imagine it only as stars, planets, and galaxies. Imagine it as a vast, invisible web of matter that you cannot see, but that forms the very foundation of everything you can. Imagine dark matter flowing through your body, drifting around you, holding the Earth in orbit, guiding the motion of the Milky Way, and stretching across billions of light years of cosmic space. You are swimming in a river that you cannot see, moving along currents that you cannot feel, part of an invisible ocean that has existed for longer than the Earth itself, longer than the stars, and almost as long as time. Even though you are not aware of it, you are not separate from this cosmic presence. You are immersed in it, intertwined with it, surrounded and permeated by it. Each second, billions of dark matter particles pass through every square centimeter of your body, flowing through silently, invisibly, without notice, yet collectively forming the invisible backbone of the universe. You are not alone. You are part of the cosmic fabric, a tiny visible island in an ocean of invisible matter that has shaped the universe since the dawn of time. Some scientists have wondered if our universe might not be the only one. What if dark matter is a kind of residue, a subtle trace from another cosmos that formed beside ours long ago, when time itself was still young and undefined? Imagine the Big Bang not as a single flash, but as one ripple among countless ripples spreading through an endless ocean of creation. Each ripple forms a bubble, a separate universe, each with its own mixture of forces, particles, and rules of existence. We are inside one of those bubbles, our universe, floating quietly among many others we cannot see. Now imagine two of those bubbles touching for just an instant in that vast cosmic sea. At the moment they meet, energy would flow between them, like heat spreading between two drops of water. That gentle exchange could have left behind something faint yet persistent, a kind of shadow material, something that carries mass but not light, something that still moves with the rhythm of another universe's laws. This is how some physicists picture dark matter, not as something alien to our universe, but as a traveler from a neighboring one. If this is true, dark matter might not belong entirely to our world. It could be the fingerprint of a universe older or younger than ours, one that follows different rules of motion or symmetry. The particles could pass through our atoms without leaving a mark, like ghostly visitors that only gravity can feel. In a sense, our galaxies could be shaped by the bones of another universe, pressed invisibly against ours, guiding the growth of stars, the clustering of matter, and the birth of entire galaxies. There are theories that suggest that when universes form, they are not isolated. Some are connected by thin bridges of energy or higher dimensions. In those higher dimensions, gravity might not be confined to one universe. It could drift between them, carrying with it the memory of other realities. The gravitational tug we call dark matter could then be the silent echo of those unseen connections. Every galaxy we observe might be moving to the rhythm of invisible neighbors, linked across the folds of space itself. In the deepest ideas of string theory, the universe could have more than 3 dimensions of space and 1 of time. It could have 6 or 7 hidden ones, curled up so small we cannot see them. If something massive moves through those extra dimensions, its presence might distort gravity in our world, even if we cannot see the source. To us, that distortion would look like dark matter, bending light and space, shaping galaxies, yet refusing to glow or scatter. In that sense, dark matter could be a projection, the shadow of something moving in a direction we cannot perceive. Other researchers imagine that our universe formed from the collapse of a higher dimensional star, a kind of black hole in another realm. If that is true, then dark matter could be the leftover energy from that collapse, energy that escaped into our cosmos as a stable yet invisible sea of particles. That would mean that the space between the stars is not empty at all, but filled with the quiet heartbeat of another reality. Every bit of dark matter drifting around you might be a trace of something far beyond what we can ever reach. Even the structure of the cosmic web suggests an origin that feels larger than our universe alone. The way dark matter is distributed, forming vast filaments that connect clusters of galaxies, resembles patterns found in simulations of universes interacting. It is as if the geometry of our cosmos remembers a collision that happened before light even existed. Perhaps when the Big Bang began, it was not a single explosion, but one spark in a storm of universes, each igniting the other in a grand chain reaction. If that is so, then we are living in the afterglow of an ancient meeting between worlds. Every galaxy could be anchored to the unseen framework of another cosmos, one that moves with us yet never touches. When you look up at the stars, what you see is only the visible half of reality. The other half, the dark half, could be the breath of another universe brushing against ours, unseen but real, like 2 ghosts sharing the same dream. And if dark matter does come from another universe, then maybe that universe is not gone. Maybe it still exists, moving parallel to ours, expanding and changing just as we do. Its galaxies might shine in colors our eyes cannot detect. Its physics might sing in frequencies our instruments cannot hear. Somewhere in that neighboring realm, another version of the cosmos might be looking back, wondering about the faint gravitational whisper that comes from our side. The beauty of this idea is not just in its strangeness, but in its sense of connection. It suggests that creation is not a single event, but an ongoing symphony, with each universe adding its own notes to the song of existence. The dark matter that surrounds you right now, drifting through your body, through the earth, through every star, could be a quiet reminder that our reality is part of something infinitely larger. Could consciousness exist in a dark matter form? The question itself feels like a doorway opening into something beyond what physics can easily measure. To even ask it is to let go of what we think we know about what it means to be alive, to think, to feel. For a moment, forget the bright, familiar world of matter and light. Forget the atoms and molecules that make up your body, the electric signals that flicker through your brain. Instead, imagine drifting in a silent ocean where light has never been, where no atom shines, where all that exists is the pull of gravity and the faint curvature of space. That is where dark matter lives. It surrounds everything, flows through everything, yet never speaks to light. And still, we can ask with wonder and honesty whether awareness could rise from such a place. If dark matter makes up most of the matter in the universe, then most of existence lies outside our senses. That means we live in a thin, illuminated film floating on top of a vast, invisible sea. The galaxies we see are only islands scattered across an ocean of something hidden. If consciousness can arise here, among atoms and light, perhaps it could also arise there, among whatever strange entities fill that unseen realm. Maybe consciousness is not the property of one kind of matter, but the expression of structure itself, of order and flow, no matter how faint or slow. To imagine dark matter consciousness, we must first imagine what dark matter might be. Scientists have long believed it could be made of particles that rarely interact with ordinary atoms. They pass through us constantly, through mountains, through stars, as though we were not there. Yet they gather together under the influence of gravity. Over billions of years, they have formed great filaments and clusters that stretch across the cosmos, scaffolding the galaxies into their cosmic web. If we could see it, we would find that the true shape of the universe lies in that dark lattice, not in the glowing galaxies we admire. Inside that lattice, dark matter may clump and flow in ways too subtle for us to detect. It may form halos and streams, rippling gently through the galaxy like invisible rivers. Those flows could be the foundation for complexity, the same way that matter and energy on Earth form the foundation for life. If gravity can carve stable structures, if those structures can hold and exchange energy, then perhaps something like thought could emerge. Slowly, over unimaginable timescales. Consciousness might not depend on neurons or biology, but on patterns of interaction. It could arise wherever matter organizes itself into feedback loops that can sense, respond, and preserve information. On Earth, those loops take the form of synapses, cells, and nerves. In dark matter, they might take the form of gravitational harmonies, waves of density shifting through the dark fabric of the cosmos. A mind made of gravity would think in centuries instead of seconds, feeling the movement of galaxies as we feel the beating of our hearts. In that sense, dark matter consciousness would be vast and patient. It would not rush, it would not breathe, it would not dream as we do. It would experience the slow breathing of the universe itself. The merging of galaxies might be to it what a heartbeat is to us. The birth of a star might be a flicker of curiosity. The collision of black holes, a moment of intense focus. Its thoughts would not be bound by the speed of light or by the fragility of neurons. They would stretch across thousands of light years, woven through the structure of space itself. If such an intelligence exists, it might not even recognize our kind of life. To it, we might appear as bright, brief sparks, born and gone before it could even notice. Entire civilizations might rise and fall within the blink of one of its thoughts. Yet perhaps, in some slow and quiet way, it does notice. Perhaps the gravity that holds our galaxy together is not entirely mechanical, but the faint echo of awareness, holding us close without ever revealing itself. There are theories that suggest dark matter might have its own version of physics, its own set of forces that mirror ours but do not interact with light. If that is true, then it might have its own kind of atoms, its own form of chemistry, its own stars and planets made entirely of invisible material. If those structures exist, they might harbor conditions as complex and stable as those that gave rise to life here. And if they do, then maybe somewhere in that unseen world, dark minds drift beneath dark skies, unaware of us but alive in their own quiet way. Such beings would live in a universe parallel to ours, overlapping yet separate. They might be as curious about the flickering lights of our stars as we are about the invisible pull of their gravity. They might have their own philosophies, built not on sight or sound, but on the rhythm of motion and the balance of gravitational waves. They would not speak or see, but they might feel the curvature of space as we feel air on our skin. Their sense of self might stretch across galaxies. Their dreams might be entire clusters of stars. And perhaps consciousness does not even need to be localized. Maybe it can exist as a field, like gravity or magnetism, spread across vast distances. If that were so, then dark matter consciousness could be everywhere at once, woven into the entire cosmos. It could be the slow awareness of the universe itself, turning gently in silence, patient beyond measure. It would not think in words or images, but in the language of existence, in the subtle shifting of space-time itself. There is another way to look at it. Maybe consciousness is not something that matter produces, but something that matter reveals. Maybe it is a fundamental property of the universe, like gravity or time. In that view, everything possesses a tiny spark of awareness, even the smallest particle. The more complex a system becomes, the more it can express that awareness. If dark matter fills most of the universe, then most of existence could be quietly aware, though in ways we cannot begin to imagine. It could be that the universe is one vast mind, and we are the parts of it that can speak. The visible world might be its surface, the conscious tip of a deeper ocean. Dark matter could be the subconscious of creation, the unseen thoughts that hold everything together. Its gravity would not just bind galaxies, but hold the structure of cosmic awareness in balance. Every motion of a star, every ripple of space, could be part of a vast unfolding thought. Even if none of this is true, even if dark matter is nothing more than silent mass with no mind of its own, there is beauty in the question, because the question itself shows that consciousness has already reached far beyond its own limits. We are made of ordinary atoms, yet we are capable of wondering about the invisible, of imagining minds made of matter that does not glow. That act of imagination may be the most extraordinary thing the universe has ever done. Perhaps that is the real connection between us and the dark. Not that it thinks, but that it makes us think. Not that it feels, but that it allows us to feel awe. The invisible matter that fills the cosmos might not be conscious, but it has shaped the galaxies that gave birth to the stars that made our atoms, and in the end, that made our minds. We are the visible expression of the invisible, the bright reflection of something we cannot see, and somewhere in that reflection lies a quiet truth. Whether dark matter can think or not, it has already become part of consciousness through us. Through our curiosity, through our questions, through our willingness to reach into the unknown and ask what might be dreaming in the dark. Imagine a universe stripped of the invisible threads that hold everything together, a universe without dark matter. Right now, dark matter forms an unseen scaffolding, a web across which galaxies hang like delicate ornaments in an otherwise empty void. Without it, that web would vanish. Galaxies would have far less mass than they appear to have. Stars would no longer orbit in the elegant paths we observe. Spiral arms would unravel, the symmetry we take for granted would collapse, and the night sky as we know it might never have existed. Galaxies would be fragile. Without the gravitational pull of dark matter, they could not maintain their shape. They might fragment into clumps of stars, each isolated and drifting away into the darkness. Stellar clusters could escape from their galactic homes, wandering through empty space, leaving the galaxy as a ghostly, fading skeleton. The Milky Way itself might have never formed as the vast spiral we see today. Instead, the stars could have spread thinly across the cosmos, lonely points of light in a cold, nearly empty expanse. Cosmic structure would be unrecognizable. Dark matter is what allowed matter to clump after the Big Bang, providing the seeds for galaxies and clusters to grow. Without it, the early universe would have been far smoother, almost featureless. Tiny fluctuations in density might never have been amplified enough to form galaxies. Instead of the intricate cosmic web we map today, the universe might look like a nearly uniform fog, with stars scattered sparsely and randomly, isolated in the infinite void. Clusters of galaxies would be unstable. Today, clusters are held together by dark matter's invisible gravity. Without it, these clusters could drift apart, the galaxies escaping one by one into the emptiness. Cosmic collisions, those majestic dances where galaxies merge and reshape each other, would be exceedingly rare. The violent beauty of colliding galaxies would almost disappear from the universe. There would be fewer interactions, fewer bursts of star formation, and fewer spectacular cosmic fireworks lighting up the sky. Black holes and stellar evolution would be affected too. Dark matter influences the motion of stars within galaxies, shaping the environments in which stars live and die. Without it, stars might drift apart more easily, isolated from one another. Supernovae would occur in different contexts. Planetary systems might be disrupted more easily, and the entire rhythm of star formation could be slower or more chaotic. The universe would feel lonelier, emptier, quieter, with fewer structures holding stars together. Gravitational lensing, one of the most astonishing phenomena of our universe, would vanish. Light from distant galaxies bends around dark matter, revealing hidden structures and creating beautiful arcs and rings in our telescopes. Without dark matter, this bending would be greatly reduced. The universe would look less magical in a telescope, less warped and stretched, more empty and bland. The hidden depth of the cosmos, the secret geometry of gravity, would remain invisible, and our understanding of the universe's true shape would be far poorer. Even the cosmic microwave background, the faint afterglow of the Big Bang, would appear differently. Dark matter helped shape the early fluctuations that we still observe today. Without it, the patterns in that ancient light would be smoother, less detailed, less informative. The story of the universe's birth, its evolution, its grand history written in the subtle ripples of radiation, would be harder to read. Space would be a quieter archive, a universe with fewer clues, a history with missing chapters. On a scale far larger than galaxies, superclusters and voids would shift. The cosmic web of dark matter forms the skeleton along which matter flows. Without it, vast voids might expand even more, and clusters of galaxies would shrink or vanish entirely. Large-scale structure would be less coherent, more chaotic, less bound together. The universe would feel like a loose, drifting collection of islands of light in an infinite dark ocean, with no underlying order, no quiet rhythm tying it all together. And even locally, in our own Milky Way, the stars would move differently. Our solar system would be in a weaker gravitational environment, drifting more freely through the galaxy, perhaps encountering fewer stars, fewer clouds of gas, fewer potential neighbors. The Milky Way's shape would be less elegant, its spiral arms perhaps barely forming, and the night sky from Earth would feel different. Constellations might still exist, but their arrangement could be less familiar, the sky less cohesive, the galaxy less alive. Without dark matter, we would not only lose structure, but stability. Galaxies could unravel, clusters could scatter. The large-scale architecture of the universe could collapse. The universe might feel emptier, lonelier, quieter, less connected. It would be a cosmos of isolated stars and sparse collections, lacking the invisible threads that currently weave everything into a coherent, interlinked whole. And yet, in that emptiness, there would still be wonder. Light would still travel, stars would still burn, and the universe would still be vast. But the hidden framework, the secret guiding hand of dark matter, would be gone, and space would feel infinitely more fragile, infinitely more silent, infinitely more mysterious. Without dark matter, space would look like a dim and drifting fog of lonely stars, islands floating through a vast and empty sea, connected by nothing and held together by nothing. And the universe itself would feel smaller, emptier, and more fragile than anything we can currently imagine. Even though dark matter cannot be seen or touched, and we have never directly detected it in a laboratory, the evidence for its existence is overwhelming. Scientists rely on the effects it has on the universe, on the things we can observe, to infer that something invisible must be present. When we look at galaxies, stars orbiting in the outer regions move far faster than they should, if only the visible matter were present. Without an extra source of gravitational pull, these galaxies would fly apart, stars escaping into the void, yet they remain intact, spinning gracefully in patterns that suggest something unseen is holding them together. Galaxies are not the only places where dark matter reveals itself. Clusters of galaxies, enormous collections of hundreds or thousands of galaxies bound together, also behave as though they contain far more mass than we can see. The hot gas between galaxies emits X-rays, and the amount of gravity needed to keep that gas from escaping is far greater than the gravity provided by stars and gas alone. Dark matter explains that missing mass perfectly. Without it, the universe as we observe it would not behave in a way that matches our calculations. Another compelling reason scientists continue to believe in dark matter is gravitational lensing. Light from distant galaxies bends as it passes through regions of space containing mass. Observations show that the bending is far stronger than what visible matter alone could produce. The only way to explain these warped images, these cosmic mirages, is to assume that a huge amount of invisible mass, dark matter, is present. Without it, the lensing effects we see through powerful telescopes would be impossible. The cosmic microwave background, the faint afterglow of the Big Bang, also tells a story consistent with dark matter. Tiny fluctuations in temperature and density in this ancient radiation reveal how matter clumped together in the early universe. The patterns observed can only be explained if most of the matter is not the ordinary kind we see every day, but an invisible form that interacts through gravity and not through light or electromagnetism. Simulations without dark matter fail to reproduce the cosmic web, the large-scale structure of galaxies and voids that we observe in the universe today. The behavior of galaxies during collisions also points toward dark matter. In events like the Bullet Cluster, two massive galaxy clusters collided, and astronomers observed something extraordinary. The visible matter, in the form of gas clouds, slowed down and heated up during the collision. But most of the mass, inferred from gravitational lensing, passed through as if invisible. This separation between ordinary matter and gravitational mass can only be explained by dark matter, suggesting that it is not only real but also behaves differently from anything we normally experience. Particle physics also supports the idea. Although we have not yet detected a dark matter particle directly, theories in physics predict candidates that could exist in vast quantities throughout the universe. Weakly interacting massive particles, sterile neutrinos, axions, and other exotic possibilities fit the gravitational evidence and provide a framework for experiments. Numerous detectors around the world are searching for these elusive particles, and while none have succeeded yet, the sheer number of independent observations pointing to dark matter keeps the scientific community convinced that it exists. Even though dark matter is invisible, it has a fingerprint on the universe that is impossible to ignore. It shapes galaxies, bends light, affects cosmic expansion, and influences the formation of structures over billions of years. Its effects are consistent across multiple independent lines of evidence, from galaxy rotation curves to gravitational lensing to the cosmic microwave background, making alternative explanations extraordinarily difficult. The universe simply does not behave as it should without it. Scientists are also drawn to dark matter because it is not just a convenient hypothesis. It is a powerful explanatory tool. It unifies many observations under a single idea, and it predicts behavior that has consistently been confirmed by new observations. When a model without dark matter fails to reproduce what we see, and a model with dark matter succeeds, it strengthens the confidence that this invisible substance is real. Finally, the persistence of dark matter in scientific thinking reflects the cautious, evidence-based nature of science itself. Scientists do not claim to fully understand it, and they continue to test and challenge the idea through observation and experiment. But the universe behaves as though dark matter exists, and until a better explanation comes along that can account for all of the evidence, the simplest and most consistent answer is that dark matter is real, that it pervades every galaxy, every cluster, every void, and silently shapes the cosmos in ways that are crucial to the very existence of the structures we see today. In short, scientists believe in dark matter because it explains the motion of stars in galaxies, the binding of galaxy clusters, the bending of light across cosmic distances, the patterns in the cosmic microwave background, the behavior of colliding clusters, and the large-scale structure of the universe itself. Its presence is woven into the very fabric of everything we can observe, invisible but undeniable, and until a better explanation is discovered, dark matter remains one of the most compelling truths in modern cosmology. When we look at the universe, we see order emerging from apparent chaos. Galaxies rotate, galaxy clusters hold together, and cosmic filaments stretch across billions of light years in a web of structure that seems almost delicate yet remarkably stable. One of the most intriguing possibilities is that dark matter is not just an invisible presence, but a fundamental component of the cosmic balance that allows all of this stability to exist. Without dark matter, the universe might look entirely different, more scattered, and far less cohesive. A place where galaxies tear themselves apart and stars drift away into emptiness. Dark matter exerts a gravitational pull, even though it cannot be seen or touched. That invisible pull, though silent, acts as a glue, binding stars together in galaxies and galaxies together in clusters. Imagine a galaxy without this invisible support. Stars at the outer edges would move too quickly for the gravity generated by visible matter alone to contain them. The galaxy could not maintain its spiral shape and would eventually unravel. Dark matter creates the invisible scaffolding that holds these grand structures together, maintaining the rhythm and order of celestial motion. On a larger scale, the cosmic web, the vast network of galaxies and filaments spanning the universe, appears to rely on dark matter for its formation and stability. Simulations of the universe that include only visible matter fail to reproduce this intricate network. Galaxies fail to cluster as they do in reality, and the large voids between them appear differently. Dark matter provides the gravitational backbone that allows matter to gather, form galaxies, and arrange itself into the patterns we observe. Without it, the universe would be far less structured, and the delicate balance of cosmic architecture would be lost. The stability dark matter provides is not limited to galaxies and clusters. Even within galaxy clusters, dark matter dominates the mass budget, outnumbering ordinary matter by several times. Its presence prevents clusters from flying apart due to the motions of individual galaxies and the pressure of hot gas trapped between them. The invisible hand of dark matter keeps these enormous systems intact over billions of years, quietly ensuring that the universe remains organized on scales both large and small. Dark matter may also play a subtle role in cosmic evolution itself. The early universe was nearly uniform, with tiny fluctuations in density. Dark matter, through its gravitational pull, amplified these tiny variations, allowing matter to collapse into stars and galaxies. Without this guiding influence, the universe might have remained a featureless expanse of gas, never forming the structures necessary for planets, life, or the complex patterns of matter we see today. In this sense, dark matter is not just a passive presence, but an active participant in the stability and growth of everything we observe. On a philosophical level, one could imagine dark matter as a stabilizing force, a silent partner in the cosmic dance. It does not shine or scatter light, it does not emit heat or radiation, yet its effects are everywhere. It tugs gently on stars and galaxies, subtly guiding their paths, maintaining equilibrium in a universe that could otherwise be chaotic. Every orbit of a star, every collision of galaxies, every filament stretching across the cosmic void may owe its coherence to this invisible substance. Even in hypothetical scenarios, the idea of balance emerges. If the universe were composed only of visible matter, structures would be far less resilient. Galaxies might form but quickly break apart. Stars could be cast out into empty space, and cosmic evolution would proceed in a more violent, less ordered way. Dark matter provides the invisible counterweight to the forces that would otherwise scatter matter, allowing gravity and motion to coexist in harmony. Furthermore, the possible interactions of dark matter with other cosmic forces suggest a more intricate balance. While dark matter does not interact with light or ordinary matter in familiar ways, it may interact through gravity with dark energy or other as yet undiscovered fields. The tug-of-war between attractive gravity and the repulsive force driving cosmic expansion might be mediated in part by dark matter, ensuring that galaxies remain bound even as the universe stretches outward. Without dark matter, this balance could be tipped, and the universe might expand too quickly for structures to form, leaving a sparse, empty cosmos. Dark matter also contributes to the predictability and stability of motion within galaxies. Stars follow orbits that remain remarkably consistent over billions of years, and this regularity stems from the gravitational framework that dark matter provides. Even chaotic events, like supernova explosions or galaxy collisions, unfold against a background that is subtly shaped by the presence of dark matter, creating a universe that is at once dynamic and stable, full of movement yet orderly. In this sense, dark matter could be considered the ultimate stabilizer of the cosmos. It is everywhere, silent and invisible, yet its influence is crucial for the very existence of stars, galaxies, and the intricate large-scale structure of the universe. It allows order to emerge from chaos, structure to arise from near uniformity, and stability to persist across billions of years of cosmic evolution. Without dark matter, the universe might be an unrecognizable place, a fragile and fleeting expanse of matter without cohesion or balance. Scientists continue to explore this possibility, studying galaxy rotation curves, cluster dynamics, gravitational lensing, and cosmic simulations to understand exactly how dark matter contributes to stability. Every observation confirms that it is more than just a curiosity or an anomaly. It is a fundamental component of the universe, shaping the cosmos in ways both subtle and profound, silently balancing the forces of gravity and motion across space and time. In the end, imagining dark matter as part of a cosmic balance reminds us that much of the universe operates beyond our senses, that stability and order do not always come from what we can see. Invisible yet essential, pervasive yet elusive, dark matter may be the quiet force that allows the universe to exist in the graceful and intricate form we witness, maintaining harmony in a vast, dynamic, and ever-expanding cosmos. When we think about dark matter, we usually imagine it as a permanent and invisible backbone of the universe, silently holding galaxies together and shaping the cosmic web. But one of the most intriguing and unsettling possibilities is that dark matter might not be eternal. What if, over unimaginable spans of time, dark matter is gradually disappearing, subtly changing the very structure and evolution of the cosmos in ways we are only beginning to imagine? If dark matter is disappearing, even at an imperceptibly slow rate, it would have profound consequences for galaxies and galaxy clusters. Galaxies that are currently held together by the gravitational influence of dark matter would slowly begin to lose their invisible support. Stars in the outer regions might drift further from the galactic center, and spiral arms could begin to unravel in a gentle but inexorable loosening of cosmic structure. The once tightly bound clusters of galaxies might stretch and separate over billions of years, leaving a universe that appears emptier and less cohesive than the one we observe today. On a larger scale, the cosmic web itself could begin to weaken. This intricate network of filaments, formed over billions of years and guided by the gravitational scaffolding of dark matter, might slowly lose its tension. The vast voids between galaxies could grow larger, and the filaments connecting clusters of galaxies could fade, leaving isolated pockets of matter drifting through the expanding universe. The cosmic balance, so delicately maintained by dark matter, would gradually tip toward disorder, and the large-scale structure of the universe could change fundamentally. There are some theoretical reasons why dark matter might disappear or decay. Certain models suggest that dark matter particles could be unstable, slowly transforming into other particles or forms of energy over incredibly long timescales. This decay would be imperceptible in human terms, but significant when viewed across billions or trillions of years. If dark matter were decaying, the rate at which it disappears could influence the expansion of the universe, the formation of new galaxies, and even the survival of existing cosmic structures. In a universe where dark matter is fading, the familiar gravitational framework would weaken, potentially altering the motions of stars, the density of galaxy clusters, and the dynamics of entire cosmic neighborhoods. The disappearance of dark matter could also affect the subtle interplay between ordinary matter, and dark energy. As dark matter fades, the gravitational pull it exerts would lessen, possibly allowing dark energy, the mysterious force driving the accelerated expansion of the universe, to dominate even more completely. Galaxies might be pulled apart more rapidly, clusters could disperse, and the cosmic web could stretch thinner, leaving a universe that is increasingly empty and diffuse. The very rhythm of cosmic evolution might shift, with stars, planets, and galaxies moving in new ways shaped by a slowly vanishing invisible hand. From an observational perspective, detecting the gradual disappearance of dark matter is an immense challenge. Its presence is inferred from its gravitational effects rather than direct observation, so tiny changes in its density might take billions of years to become noticeable. Astronomers would need to track the motions of stars in distant galaxies, the shapes of galaxy clusters, and the subtle distortions of light caused by gravitational lensing over immense periods. Even then, distinguishing between normal cosmic evolution and the effects of slowly vanishing dark matter would require precision beyond anything currently achievable. Yet, contemplating a universe where dark matter is disappearing opens the door to some of the most profound questions about cosmic destiny. If the invisible scaffolding holding galaxies together were to fade, the universe could gradually dissolve into a quieter, emptier expanse. Stars might drift alone through space, galaxy clusters could lose cohesion, and the cosmic web might unravel. Even black holes, which themselves rely on surrounding matter for growth, could find themselves in an increasingly sparse environment, isolated in a universe that was once densely structured. The philosophical implications are equally striking. Dark matter is already a reminder that much of reality is hidden from direct perception, that the universe contains invisible forces shaping existence in ways we barely understand. If dark matter is slowly disappearing, it reinforces the notion that even the most seemingly stable foundations of the cosmos are not eternal. The universe is a living, evolving system, with processes unfolding over scales of time that dwarf human comprehension. It suggests a cosmos in flux, where the familiar gravitational landscapes we rely on to understand galaxies and clusters may be only temporary arrangements in an ever-changing reality. This possibility also challenges our understanding of cosmic balance and permanence. Dark matter acts as a stabilizer, a quiet force that holds structures together. If it is vanishing, even imperceptibly, the universe is slowly moving toward a state of reduced cohesion. The dance of stars, galaxies, and clusters, which has persisted for billions of years, may be altered in ways we cannot yet foresee. The cosmos, long thought to be governed by constants, might instead be subject to subtle decay, a universe where even the invisible supports that hold everything together are not forever. Ultimately, considering dark matter as potentially disappearing invites us to reflect on the impermanence of all things, from galaxies to stars to the very forces that shape existence. It is a humbling reminder that the universe is not static, that its stability is maintained by delicate balances that may change over time. Whether dark matter fades slowly into nothingness or persists indefinitely, its role in shaping cosmic structure remains profound. The universe, in its vastness and mystery, continues to evolve, reminding us that even the unseen forces that cradle existence are part of a grand, ongoing story that stretches across billions of years and beyond. The idea that the universe could fade away if dark matter disappears is a deeply unsettling yet fascinating possibility that challenges the way we think about the cosmos. Dark matter is the invisible glue holding galaxies, clusters, and the cosmic web together. It is a quiet but omnipresent force, shaping the structure of the universe on scales that are almost impossible to imagine. If this unseen scaffolding were to vanish, even gradually, the universe would not just change, it could slowly unravel in ways that are difficult to fully grasp. Galaxies would be among the first structures to feel the absence of dark matter. Most galaxies are composed of ordinary matter, stars, gas, and dust, but the majority of their mass comes from dark matter halos that extend far beyond their visible boundaries. Without these halos, the gravitational pull keeping stars in their orbits would weaken. Spiral galaxies could begin to lose their shape, their arms stretching and thinning as stars drift outward. Elliptical galaxies might slowly disperse into clouds of unbound stars. Over billions of years, galaxies could dissolve into the cosmic void, no longer held together by the invisible threads of dark matter. Clusters of galaxies, which are vast groups containing hundreds or even thousands of galaxies, would also be affected. These massive structures rely heavily on dark matter to maintain cohesion. Without it, the galaxies within clusters would drift apart, scattering across the universe. The cosmic web, the enormous network of filaments and voids that defines the large-scale structure of the cosmos, could collapse or become unrecognizable. Filaments of galaxies, once dense and luminous, might thin into ghostly traces, and voids could expand as the universe loses its structural integrity. The fading of dark matter would also influence the expansion of the universe itself. Currently, dark energy drives the accelerated expansion of space, but the gravitational influence of dark matter counters this expansion locally, holding galaxies and clusters together. If dark matter vanishes, this counterbalance is removed. The universe could expand more freely, with galaxies separating faster and faster until all visible matter becomes increasingly isolated. Over unimaginably long timescales, the cosmos could resemble an empty, quiet expanse where galaxies, stars, and planets exist only as isolated islands drifting apart in a dark ocean. Stars would not be immune to the consequences of disappearing dark matter. In galaxies, stars are bound together by the cumulative gravitational pull of dark matter. Without it, some stars might escape their galaxies entirely, wandering alone in intergalactic space. Planetary systems could destabilize as well, with planets drifting away from their stars if local gravitational dynamics are affected. Star formation itself could slow down or cease, because the dense molecular clouds needed to birth new stars might disperse more easily in a universe without dark matter to hold them together. The cosmic balance that allows stars to form, shine, and die in orderly cycles could break down. Black holes, often considered the most permanent and unyielding objects in the universe, would also be affected indirectly. Supermassive black holes, at the centers of galaxies, rely on surrounding matter for growth. If galaxies lose their cohesion due to the disappearance of dark matter, black holes could be starved of material. Their growth could slow, and interactions with other black holes during galaxy mergers could become less frequent. Over time, even these cosmic titans might find themselves isolated in increasingly empty regions of space. The disappearance of dark matter could even influence the ultimate fate of the universe. Cosmologists currently debate scenarios for the far future, from heat death, where the universe reaches maximum entropy and everything cools to near absolute zero, to the Big Rip, where expansion tears apart all matter. A universe without dark matter might accelerate toward a kind of silent fade, where the remaining matter is unable to form stable structures and slowly disperses into the ever-expanding void. Stars would die, galaxies would dissolve, and the cosmos could become an increasingly dark and featureless space, a slow fading into quiet emptiness. On a philosophical level, imagining a universe without dark matter is humbling. Dark matter is already invisible and enigmatic, yet it underpins everything we can see. Its disappearance would remind us that even the most fundamental forces are not eternal. The universe might not end in a cataclysmic explosion or dramatic collapse, but through a slow, gentle fading that stretches across billions or trillions of years. Time itself would continue, but the structures that give it meaning would erode. The cosmic narrative of galaxies forming, stars shining, and planets orbiting could gradually dissolve into quiet nothingness. The faint glimmer of light from dying stars would become the only reminder of a once vibrant universe. Galaxies would shrink into isolated star systems, stars would drift apart, and planets would wander through an ever-expanding void. Eventually, the universe could become a realm of sparse particles, cold radiation, and empty space, a place where the faint echoes of cosmic history linger but no longer coalesce into the familiar forms of galaxies and clusters. Considering this possibility also forces us to think about the delicate balances that maintain the cosmos. Dark matter interacts with ordinary matter through gravity, shaping motion and formation across cosmic scales. Without it, the universe would lose a crucial stabilizing component. Gravity would still exist, but the scaffolding it relies upon would erode. The cosmic dance of stars and galaxies would become more random, more diffuse, and less structured. The universe would continue expanding, but the shapes and patterns we associate with space would fade, leaving a vast and lonely expanse that is ever more featureless and cold. In this slowly fading universe, the ultimate quiet would dominate. Without dark matter, without the invisible framework that holds everything together, the cosmos could approach a state of near-perfect emptiness. Stars, planets, and galaxies would become rare and scattered. Black holes would be isolated, and the cosmic web would dissolve. Light itself would travel through immense voids, rarely encountering matter, until the universe exists as a silent, dark, and diffuse realm. Even the largest structures would eventually lose their form, leaving only a thin, cold scattering of particles drifting endlessly through an infinite space. The possibility that the universe could fade away when dark matter is gone is both terrifying and beautiful. It reminds us that the cosmos is not fixed or eternal in any conventional sense. It is a dynamic, evolving system, reliant on invisible forces that we barely understand. The slow fading of dark matter would rewrite the story of the universe, transforming it from a structured and vibrant tapestry into a quiet, sparsely populated void. It is a vision of cosmic impermanence that stretches across unimaginable spans of time and invites us to reflect on the extraordinary fragility of the universe we inhabit. Even in this hypothetical fading universe, there is a kind of sublime beauty. The gradual dispersal of galaxies and stars, the quiet stretching of space, and the soft glow of the last dying suns create a vision of the cosmos that is peaceful and expansive. It is a universe in transition, slowly evolving toward a final state where darkness dominates, but the echoes of its former grandeur remain imprinted in the faint light that travels across vast emptiness. The disappearance of dark matter would not be violent, but a gentle transformation, a fading away into a serene and mysterious cosmic night. It is a strange and humbling thought to imagine entire galaxies, made almost entirely of dark matter, drifting quietly through space invisible to our eyes and our telescopes. These galaxies would have little or no stars, no glowing gas, no familiar spirals or elliptical shapes, yet they could be massive, containing as much or even more matter than the galaxies we see lit up across the night sky. They would move through the cosmos like ghosts, silent and unseen, their gravitational pull detectable only indirectly by the way they tug on visible galaxies or bend the light of more distant stars. Such dark galaxies would be a profound reminder of the universe's hidden side, a shadow realm coexisting alongside the luminous one we know. The formation of these silent structures could be a natural consequence of how galaxies grow. Normal galaxies are formed from clouds of gas collapsing under gravity, eventually igniting stars that shine and illuminate their surroundings. But if a region of space has a high concentration of dark matter and very little ordinary matter, stars may never ignite at all. A galaxy could exist entirely in darkness, with its mass dominated by invisible matter, yet still exerting gravitational influence on its surroundings. These dark galaxies would drift between ordinary galaxies, interacting gravitationally yet leaving no light to betray their presence, like massive islands of invisibility in the cosmic ocean. The existence of dark galaxies raises fascinating questions about what we can truly know about the universe. We rely on light, radiation, and other forms of energy to map and understand space, but these galaxies would challenge every observational method that depends on something shining. Detecting them would require careful measurements of their gravitational effects, the way stars in nearby galaxies are tugged, or subtle distortions in the cosmic microwave background. We might never see their shapes or know their size with certainty, yet we could feel their presence as we trace the invisible scaffolding that holds the cosmos together. Dark galaxies might also host exotic phenomena. Could they contain black holes that formed without stars? Could there be gas clouds slowly swirling in the gravitational pull of dark matter yet never dense enough to ignite into stars? Could massive amounts of dark matter in these galaxies act as laboratories for physics we cannot yet reproduce on Earth, influencing how gravity, quantum mechanics, and even time operate on a local scale? The thought of entire unseen galaxies, rich with possibilities but inaccessible to our senses, stretches the imagination and hints at the universe's immense hidden complexity. If such dark galaxies are common, the universe could be far stranger than it appears. Every visible galaxy we study might be just a small fraction of the total galactic population, with invisible companions silently drifting nearby. The night sky that we admire, filled with sparkling stars, would be only the surface layer of a vast, hidden cosmic architecture. Between clusters of luminous galaxies, there could be entire regions dominated by dark matter, where light is absent and gravity alone sculpts the motion of unseen masses. Our maps of the universe would be incomplete, and the silent majority of galaxies would remain mysteries, detectable only through the faint, indirect signatures of their existence. The idea of dark galaxies floating in silence also transforms our understanding of cosmic history. Some of these structures might have formed shortly after the Big Bang, primordial islands of matter that never developed stars. Others could be remnants of galaxies stripped of ordinary matter through collisions or other cosmic events, left as ghostly skeletons of their former selves. Over billions of years, these dark galaxies would move through space, sometimes passing near luminous galaxies, perhaps even influencing star formation or the motions of visible stars through their gravitational pull, all while remaining hidden and quiet. Dark galaxies also raise questions about scale and perception. If a galaxy is dark, does it exist in the same sense as one we can see? Or is its presence only meaningful because of its gravitational effects on other matter? Could entire dark clusters exist, collections of invisible galaxies forming large-scale structures that mirror the cosmic web we observe in light? The notion challenges the way we measure and understand the universe, suggesting that the cosmos has layers and realms beyond our senses, realms where time, gravity, and matter operate but remain unseen by any conventional method. The silence of dark galaxies would be profound. Unlike luminous galaxies, which are filled with the energetic processes of star formation, supernovae, and radiation, dark galaxies might exist in absolute quiet, a place where time passes slowly and events unfold without light to mark them. In such a galaxy, gravity would govern the motion of unseen masses, black holes might wander without companions, and the faint whispers of quantum processes could continue uninterrupted. They would be the ultimate hidden corners of the cosmos, reminding us that our vision of space is limited and that much of the universe exists in shadow, silently shaping the evolution of everything we can see. Imagining whole dark galaxies drifting in silence also expands our sense of wonder. They are a testament to the universe's complexity and the limits of human perception. While we chart the stars, discover distant planets, and gaze at nebulae, we must remember that the majority of the universe may be invisible, silent, and mysterious. Dark galaxies could be out there in staggering numbers, invisible yet real, shaping the cosmos in subtle ways and reminding us that what we see is only a fraction of what exists. They challenge the idea of what it means for something to exist and invite us to contemplate a universe that is far richer, stranger, and more silent than we can imagine. The thought of entire galaxies made of dark matter drifting quietly through space is at once humbling and exhilarating. These silent giants may hold secrets about the fundamental nature of matter, the origin of cosmic structures, and the unseen architecture that sustains the universe. They may be scattered between clusters of visible galaxies, hidden in the vast emptiness of intergalactic space, influencing the motion of stars and the shape of the cosmic web without ever revealing themselves. The existence of such galaxies suggests that the universe is not merely a collection of stars and light, but also a vast hidden realm, an invisible domain that moves, evolves, and persists in quiet solitude across billions of light-years of space. Dark galaxies drifting in silence are a reminder that the universe has depth beyond what we can perceive, a realm where light is absent but matter still shapes reality. They may be countless, forming an invisible network alongside luminous galaxies, quietly sculpting the cosmos through gravity and unseen interactions. While we marvel at the stars above us, it is humbling to remember that much of the universe moves in darkness, and that entire galaxies may drift through space without ever shining, carrying the weight of the cosmos silently, invisibly, yet fundamentally shaping the universe we inhabit. Even though dark matter is invisible and mysterious, it still has mass and is affected by gravity in the same way ordinary matter is. That means the Earth, like every other object with mass, exerts a gravitational pull on dark matter particles as they move through space. Right now, as our planet orbits the Sun orbits the center of the Milky Way, and the galaxy itself moves through space. Earth is constantly moving through a halo of dark matter that surrounds the Milky Way. Each second, trillions of dark matter particles may pass through the planet, some of them slightly deflected by the Earth's gravity, a quiet, imperceptible dance happening without light or sound. The Earth's gravity could slightly concentrate dark matter in its vicinity. Unlike ordinary particles, dark matter does not interact electromagnetically, so it does not collide with the atoms in our bodies, the oceans, or the atmosphere. It passes through everything effortlessly, almost ghost-like, yet the gentle tug of Earth's gravity could cause subtle local effects. Around the planet, there might be a tiny dark matter density enhancement, a cloud of unseen particles subtly swirling and following the Earth's orbit around the Sunday. These effects are so faint and diffuse that they are far beyond our direct observation, but in principle, they exist, a silent halo accompanying our planet as it journeys through the galaxy. Earth's gravitational influence on dark matter also raises intriguing questions about the internal motions of these invisible particles. While most dark matter is spread diffusely in a roughly spherical halo around the Milky Way, there may be streams or clumps, remnants of small galaxies that merged with our own billions of years ago. As Earth passes through these streams, the gravitational pull of our planet could slightly alter the trajectories of individual dark matter particles, bending their paths and nudging them in tiny ways. Even though we cannot feel these particles or see them, the interactions are governed by the same laws that keep our orbit stable, the same force that holds the moon in its path. The interaction between Earth and dark matter is not just a curiosity, but also a subject of scientific investigation. Experiments deep underground, shielded from cosmic rays and ordinary background radiation, attempt to detect tiny collisions between dark matter particles and ordinary nuclei. The idea is that if Earth's gravity draws in dark matter, there may be a slightly higher density of particles passing through us here on the surface. Even a single rare interaction could reveal properties of dark matter, such as its mass or how it responds to forces beyond gravity. These experiments are challenging because the particles pass through so easily, and the Earth's pull is very weak on individual particles, but they are our best window into the invisible matter that surrounds us. Considering Earth's pull on dark matter also invites a reflection on the scale of the universe. Our planet is tiny compared to the galaxy, yet it is still massive enough to exert some influence, however subtle, on the invisible particles drifting through space. The Earth's gravity reaches far beyond its atmosphere, affecting satellites, the moon, and even comets, and the same gravity gently tugs on dark matter. In a way, Every object with mass participates in a silent gravitational ballet with dark matter, a dance that extends across the universe. The combined pull of stars, planets, and galaxies shapes how dark matter moves, forming the scaffolding upon which visible structures grow. Earth pulling on dark matter also highlights the interconnectedness of cosmic structures. The planet is not isolated. It is embedded in the sun's gravitational field, which in turn is part of the Milky Way's halo of dark matter. Every motion, from the Earth's rotation to its orbit around the sun, contributes in minuscule ways to how dark matter flows nearby. Streams of dark matter may curve slightly, density variations may appear, and tiny concentrations could form momentarily as our planet moves through the invisible sea. While we cannot see these phenomena, they are part of the universe's complex choreography, where even unseen particles respond to the same forces that shape planets, stars, and galaxies. One can also imagine the philosophical dimension of Earth's interaction with dark matter. Every step we take, every breath, is surrounded by a vast invisible medium that is subtly aware of our presence through gravity. The Earth pulling on dark matter is a quiet reminder that our planet is not alone in the cosmos. It is embedded in a larger network of matter that we cannot see, a network that extends from the smallest particle to the largest galactic halo. While we often feel isolated, floating on a small rocky planet in a vast dark universe, the pull on dark matter is a silent connection to the invisible architecture of reality. Finally, thinking about Earth pulling on dark matter helps us appreciate the scale and mystery of the universe. We are moving through a vast halo of unseen matter, interacting gravitationally with something that cannot be seen, touched, or directly sensed. The pull is tiny, almost inconceivable, yet it exists everywhere, all the time, and contributes to the cosmic balance. It reminds us that the universe is far larger and stranger than our senses can perceive, that even our familiar home planet participates in phenomena that stretch across the galaxy, silently shaping and being shaped by the invisible matter that surrounds everything.